Thank you very much. Thank you for introducing. Hello. I just wanted to show you today a bit how I conduct my studies for both undergraduate and graduate students, and I would like to show this today on grippers and the robotic arm. There are two parts. One is, as aforementioned, the end effectors, and the second one, the evaluation of the additive manufacturing thereof. This was done in a several semester attempt. The students were starting with analyzing what's available so far. It is really important that one is more or less having a very close look at that what's available, because we don't want to design something which is already there. When we are just letting now go through all the commercially available end effectors, you will see that they are pretty much looking all the same, or if there are variations, then it's deriving from the very purpose. I train the students in a way that as industrial designers, we are not using off-shelf components or products in order to make a gripper, but we specifically design the gripper for a purpose. So the function is a bit less than the purpose. The purpose is in the center. And after that, we will choose the proper material and the respective fabrication technology. In order to see what's available in the market, it is a good idea to know what the industrial application will be about. Fingers are not necessarily good. I heard over the last days here that 5 fingers of the human hand are quite perfect. I have to object to that. Later I will tell you a bit about these bionic principles, or when you look at natural paragons, live paragons from nature, you always have to bear in mind that the fingers are coming from evolution. And once upon a time, about 300 million years ago, we were a primordial fish, and out of the breast flipper of this fish, the fin rays made up then later on our fingers. So it's rather a wonder that with our 5-finger hands we can operate so perfectly depending on the different tasks, and we heard it today already that this has developed the growth of our brain. So there is this feedback loop between eye, brain, arm, and hand and fingers, and you can't separate that because it all happens with motion in environment, also called mobiligence. So the training of the fingers really made our brain become big, and therefore we are capable of doing things which otherwise we could not achieve with a 5-finger hand. So looking at different tasks, we wondered how in the animal world gripping, grasping, and positioning is taking place. We have physical effects which can be derived from nature, and we have others which are purely theoretical. Also those can be, as human artifacts are free of any evolutionary burden, applied to a solution finding. So in the case you want to have a universal gripper, you have to make up what is nature doing in order to achieve the task. Well, humans are not the only ones gripping. All animals somehow do reaching, grasping, gripping, picking, and placing. When looking at that, then you will see that there are certain principles behind, always depending on the purpose of your action. And this is exactly the center meaning. The purpose you want to achieve will shape your product. Usually what you saw before with the industrial components, the grippers, they are made by engineers, and industrial designers try to approach this topic in a different way, which is purpose-driven. So in the end, industrial designers are not trying to design a wallpaper or a cladding in order to house the function, but instead having a structure which allows you to properly grip, and in itself, the purpose-driven shape is having an inner beauty. That is a different approach instead of usually cladding, housing, or covering functional parts, as usually the case with consumer products. In nature, you have always a very distinct relation between the shape and the action which is taking place. There is nothing really accidental. It is all targeted in order to perform the task, and later you will see why we picked the bird's beak. And as you see here from our colleague Witte from Technical University in Ilmenau, evolution was we were in the sea, we went on land from quadrupedal to bipedal walking, our brain evolved, the forelegs made us then move our hands. Here you see the relation between biology and engineering, and by the help of equation and calculus and rules, you can gain knowledge, and by that you can make a product in application for industry, whereas biology is more on findings. And it's very famous with Charles Darwin that looking at finches, how retrogradely evolution changed their beaks, and therefore we are looking at birds because already Rouleau in the 19th century was describing that the mechanism of a bird's beak is the same for all birds. So analyzing this, Schelling and Zimmermann, again from Technical University in Ilmenau in the 1990s, were describing a transition of the three-dimensional linkage to a two-dimensional model thereof. So in most cases, the virtual model making helps you in order to create something which can be then a new approach to gripping. In this case, it's the Watts linkage. This typical skull of a bird exemplifies where the different joints and levers are. And now looking how gripping in nature and technical applications can be superimposed. You have in the top row the design of our grippers, and in the bottom row you see the natural examples even when grasping textiles. And suction is sometimes used, but we are avoiding that because it's too easy just to operate with various pressure levels. We are more interested in direct gripping, and in some areas like here with pubic louse, you see that the grippers are differentiating even the type of hair which is being gripped. I teach the students that they should always look at images, be it from scanning electron micrographs or computer tomographs, because there is a so-called heuristic by analogy, meaning you can have initiating, form-finding moments when looking at solution areas found in nature, and when you try to reason that over into the technical world of human artifacts. There are different ways of gripping. I think about more than 10 are known to humans. The 6 most important ones you see here. And functional morphology means we are very much like a monkey, capable of doing overshot actions. That's the very reason why we are so successful as humans and as hunters. We are not forced to do undershot when we drink or throw a spear, but we can actually properly manipulate the upper quadrant. And these principles can be transformed by traditional pencil sketches to initial ideas, then transformed over to paper models, simple 2D models, pretty much like in the 1990s. And then later on, the computer-aided industrial design software is used to shape the function. In this particular case, you see the transition between the initial sketch over to the volume. I can tell you that even the kind of software you are using as designer predetermines later on the looks and the appearance of your model. I'm not mentioning any company names, but you are no longer having the freedom of choice how finally your product is going to look like when you make your decision which software tool you are employing. In this particular case, it is subdivision modeling, and this will lead to a very, very fluent, almost bionic looking final result of the geometry. Only here the friction bearings needed to be subtractively manufactured into the piece. All 3 grippers were designed in a way so that they can be only fabricated by 3D printing. This was another prerequisite, that we do a form finding which cannot traditionally or subtractively machined. Highly integrated, powered by artificial muscles, which are also co-developed, and they are industrial components capable of very many load cycles before they deteriorate. And here you see the difference between the final product printed and also the previous computer work for that. It's a pincer grip for textiles. Nowadays we have heard, that 3D printing is more or less limitless. You can do whatever you want. In this project we could prove that you have quite some limits, just as with the software. When you are going for one, you have definitely chosen a certain looks, and when you print it, then you will see what the methodology of the printing also as kind of flaws will provide. So you have to go through several cycles in order to improve the shape. Going back to the Watts linkage, you see another interpretation here for a line gripper, which is in 3 iterations optimized in order to be lighter, better, and more agile. Here you see there are 2 fingers opposing 1. This will be in a next step eliminated to only 2 opposing grippers. Then the clash and interference check, animations in virtual reality. So it's always about model making in the virtual world and checking not only stress but also the parts and the numbers, then the drives, how to incorporate them, and see how you can optimize this system further and further. It would be very difficult to imagine to do this solely on paper. So we have a completely closed digital process chain allowing to check on the geometry and improving it. Later on, this geometry will be made lighter. Here you see it is completely ripped by lines of flux of forces, and the whole component is hollow in itself. You see the slits to the side. That's necessary in order to get the metal powder out of the inner volume. What you see from the external view is the very same as if you would put a cut through these components. The ripping is also internal in order to save weight. Overall, you have here an appearance pretty much like the structures in a thigh bone, where you let the forces travel also orthogonal to the surfaces. This way here you see that transition to a spatial gripper. This one can be used for volume objects. In this case, it is self-closing and holding then the gripped object by itself. A variation of the linkage has been done, and in this way the single components were calculated in order to have the maximum gripping force at the lowest self-weight. Here an intricate cubic lattice work was incorporated to save further weight, and all components are listed in a database so that we can predict very early already the final weight. So when you are changing your design, you can predict in which way the static or dynamic forces will change on a robotic arm. The 3 grippers you are looking at here were for graduate students, so it was and is their master thesis. For the undergraduate students, we have done the respective robotic arm, also based on lightweight principles, including simplicity, so the less parts the better. And later on, during their Ph.D. studies, they are catching up on this topic again and redesigning the robotic arm, including the end effector, to their new knowledge base. By this way, you can constantly optimize. It is a so-called vertical teaching, meaning the students are participating from the first, let's say, to the 10th semester to these topics. So you have a good continuation and not a 1 semester project which will by no means capable of yielding such objects, as the students not only have to do the analysis and the actual industrial design of the components, but they also literally manufacture these pieces. So they have done up to 3 robotic arms and currently 4 robotic grippers themselves, including all metal work. And they also take advantage by using very, very modern methods of imaging, because I truly believe that only by looking at nature and compare it with human artifacts, you can intrinsically learn. It is research which is then transformed into prototypes. The design, engineering, and manufacturing is all done by the same group. You have the point grip, the line grip, and the spatial grip. We make a morphological box from which you are deciding what kind of arrays to further develop. You have the subdivision surfacing, as mentioned for the point gripper. You see that this special software is yielding a special shape, which is unique. Then you create variants, you select, and then by the help of support structures, you can print this object then in metal. The building process has to be overlooked in order to see what the shortcomings are. Then the parts need to be scrutinized. Usually we have to print several times before we are having a satisfied object. The small holes indicate the subtractive parts for the machining of the friction bearing. The line gripper, you see here the evolution. In the middle row, you see the air. These are the areas which were taken away. So the total reduction of weight was here about 50%. The support structure necessary to print these parts. Later I will show you what the resulting problems can be in printing. And then assembled, and the spatial gripper with the lattice work incorporated in the levers in order to have less mass in the massive parts. Also here support structure, and then the array. The manufacturing of the components took place by selective laser melting of titanium alloy. We were measuring the warpage and also counteracting to the warpage of the fabrication process. You are very well aware of that when you 3D print, I mean, circles do not stay circles and straights do not stay straight. So you have to look for warpage and to compensate it. And these grippers here were made down to 0.4 millimeter wall thickness internal structure. This is about the least you can get when you want to have a stable product for industry. The defects you can get are elongations, cracks from too much stress in the system, or you get stress when you are having the support structure not really in an optimal location. And also when deforming, you can have quite some problems. The overview here shows you that the point gripper and the line gripper are both pretty similar in the values, whereas the spatial gripper is a bit heavier and has more volume by nature, I would like to say. And interestingly enough is that they are all patented for one fundamental patent each, and it shows in the bottom row the contraction necessary to operate them with the artificial muscle. Here you see all three grippers are pretty much in the same solution area, derived from the principle of bird's beaks. And you see the different finger numbers, and only the spatial gripper, and this explains also the higher weight, is capable of changing radially linear, radially centric, and parallel linear and parallel centric grip, whereas the point and line gripper are fixed in the way they are gripping. All three grippers had to be, as I said, fabricated several times before the final result was satisfying. This has something to do with the methodology of the 3D printing process, and I'd like to conclude with the robotic arm, where undergraduate students were over the course of several years designing a robotic arm. In order to have our own system here, we always start looking at nature. For instance, in this case, we are having a grasshopper leg. Through scanning electron micrography, you can transfer this by computer-aided industrial design to a kinematic model. Later, we were looking at arthropods like lobsters and the different angles of the joints. And then these two findings can be, by heuristics in analogy, transferred to a new joint lever system together with exoskeleton, and this way you can check on the shape by finite element analysis, and we are getting a modular arm system derived from nature without looking like the natural paragon. I have really, from my experience, to warn, when you look at grasshoppers and lobsters, please never ever copy a natural model and later on your robot looks like your natural model. This will never work. And for several reasons it is wrong to do methodology this way. Nature grows at ambient temperatures with organic live materials. We humans, we are not using organic live materials, nor do they grow generatively, apart maybe from additive manufacturing, but we have in most cases anorganic dead objects, and we subtractively or additively make them at exothermal reactions. Totally different, therefore we can never match the shape, or we will never achieve nature's looks. But what you can do, and this is I guess the better way, you have a human artifact which looks like a machine. It's industrial looking, and again, from an industrial point of view, it is not covered by a neat sleeve or housing so that you are hiding what's inside. We want to have a machine which moves like a human. We call it anthropofunctionality. Whereas you have normally robots, also humanoid robots, they look like their counterparts, but when they move, it is like a breakdancer, like a machine. So our colleagues from the university in Jena, evolutionary biology, like Mr. Lauströer and Martin Fischer, they have, by computer tomography, analyzed a rat and by inverse kinematics doing a certain gripping motion. And this you can do also with humans in the motion lab at the university in Jena. So I ask my industrial design students always to work in a transdisciplinary mode. You get, by the help of these infrared markers and the cameras, the motion trajectory in your working space to lift up your arm. And by the help of systems control, people like Arment, they were writing a control software that our robotic arm can be moved according to the pattern of this student here. And on the right-hand side, you see the advantage of, in this case, pneumatically driven robot, meaning we don't have any electric parts. So even when this robotic arm is catching water drops and you have water all over the place, your system will not fail. This is the big advantage of fluid technology, where you don't have electricity on the external parts. Looking back on anthropofunctionality, in the upper right-hand corner, you see a lady dancer doing a pas de deux with the robotic arm. This means that the lady has been scanned by infrared motion markers, and then the control software is almost in real time superimposed with her pattern onto the arm. This way we have an industrial looking arm capable of doing human motion. The harmonic action you see here when it's doing kind of butterfly motion, and in the center this robotic arm, due to low weight and high agility, is capable of throwing dart. Again, here you see students without the infrared markers, but previously they were wearing it in order that we can see the trajectories, and this robotic arm is so capable then of accelerating up to 18 G and has a payload of about 2.5 kilograms at a velocity of up to 700 degrees per second. The gripper for the front, I was also explaining today how one was coming from point to line and space gripping based on the linkages found already in the 19th century on birds' beaks. And this yielded then for the industrial design students objects which were additively manufactured in laser sinter melting process in titanium 6 aluminum 4 vanadium alloy. And so we are having our arm and our gripper fully done ourselves and not purchased any shelf products. This here is the computer image, not the real one. So we can simulate nature also visually as industrial designers. And this is in 2 books already published. And for those of you interested in, on the right-hand side of you in front of the screen at our table, we have some prospectuses and a small booklet for you to take with you free of charge if you are interested in. And I thank you very much for paying attention. So this is our small team which came over from Europe here to Singapore to train the students further in robotic arms and grippers. Thank you very much.